So I'll start. So we're going to prove that the multiplicative group fp star is cyclic. So that's our primary goal right now. And remember, fp star means it's exactly the same thing as z mod pz star. So this is the group of numbers 1, 2, up through p minus 1 under multiplication. Mod p. And here p is a prime. Okay? So this is a fact, and I need to convince you that it's true. It's actually a special case of a more general fact. If you take any field at all and take a finite subgroup of its multiplicative group, then that is cyclic. So this is just one special case of that. And the proof that I'll give you will work in much more generality, so you might want to think, am I using anything special about the integers modulo p? And I'm really not. So this is really just a special case of something. Where the thing is that any finite subgroup of a multiplicative group of a field is cyclic. When I was a grad student at Berkeley, we had to take some exam called the prelim, and it was this was usually a question on it. So in fact, when I took it, it was a question on the exam, was to prove that. I was like, yes, that one's easy. So the proof in general is just exactly like what we'll do. It's just that I'll do things a little more carefully and assume less algebra than you need for this. By the way, the analog of this, if p isn't prime, so let's just take an example to see that. If you replace p being prime by something that's not prime, and then take and put a star there, so you get the numbers that are between 1 and n minus 1 that are co-prime to n. In this case, numbers are 1, 3, 5, and 7. If it's not prime, that's not necessarily true. It need not be cyclic. For example, here, each of these elements, when you square it, you just get 1 modulo 8. 3 squared is 9, which is 1 modulo 8. 5 squared is 25, which is 1 more than 24. 7 squared is also 1 modulo 8. So this is not cyclic. Although, let's see, so what about z mod 4z star? So it's not like an if and only if type thing. This just has elements 1 and 3. And is this group cyclic or not? Is there one element in there? So every element is a power of one element. Josh shakes his head, yes, so what element? 3, exactly. This is the group generated by 3. This notation means the group generated by. So this is generated by 3. So sometimes the multiplicative group of z mod nz is cyclic even when n is not prime. Just as a teaser in that direction, it's actually pretty tricky to prove, but z mod p to the rz star for p odd and r any power at all is cyclic. So that's kind of tricky to prove, but it's true. But it's not true when p equals 2, as you can see from this example. Okay. All right, so now I want to convince you that fp star is cyclic. So basically the question is why? Why is there some element g in fp star such that all the elements of fp star are the powers of that one element? G squared, g cubed, all the way up through g to the p minus 2. Because g to the p minus 1, that's g to the order. Actually, I should include that because I want the element 1. Seems like it's noisy outside. Somebody close the door. So why is there such a g in there? Again, it's not just some it can't be some completely trivial, obvious thing, because it's completely false if we replace p by 8. So there's something going on, some special thing that happens. And that special thing is, as is suggested here, that fp star, or sorry, that fp is a field. That's what we're going to use in order to see this. All right, so we're going to do some things with polynomials that will use the product. So the key thing about being a field, so here K is a field. A field is a collection of numbers that you can add and multiply, and whenever you multiply, like basically every non-zero element has to have an inverse. That's what it means. So field, so every non-zero element has a multiplicative inverse. And this is the case for fp star. It's not the case for z mod 8z. There are non-zero elements in here that don't have a multiplicative inverse. Can anybody think of any? Not with the star there, but just z mod 8z itself. Can anybody think of a number mod 8 that isn't 0, and it also does not have a multiplicative inverse? 2. Yeah. 2, there's no number that you can multiply 2 by, modulo 8, that gives you 1. So z mod 8z, it's a ring, but not a field. Okay, so now, just reminding you that, now let's see why this is true. So first I'll prove a proposition. So let K be a field, any field at all. In particular, we're going to be interested in FP, but this is very, very generally true. And let F be a polynomial over K, so a polynomial in one variable with coefficients in K. Then the number of roots of F in K, the number of roots of F in K is less than or equal to the degree of F. Okay, seems like a completely obvious thing that you know well, but just to let you know that there has to be something to this, notice that if you take the polynomial x squared minus 1 mod 8, so do this as a polynomial in in z mod 8z, adjoin x, so this is not a field. How many roots does this polynomial have? How many elements of z mod 8z have the property that they're a root of this polynomial? Kind of see them on the board here. You say 1, you're not right. Not all of them, because if I put 0 in here, that's not a root. There's 4. Yes, there's 4 of them. Namely, 1, 3, 5, and 7. These are all elements of z mod 8. So these numbers viewed as numbers mod 8. All satisfies polynomials. So this has 4 roots and has degree 2. So isn't that kind of weird? So that does happen if you consider general rings, but it never ever happens for any field at all. The second that you have multiplicative inverses for all the non-zero elements, you're never going to have more roots than the degree of the field. Than the degree of the polynomial. Okay, now, hopefully, you appreciate that I have to convince you of that, because you probably won't believe this proposition unless I do something more, given that I made you suspicious of it. Okay? Good? So I'm going to do some little trick that's going to use the fact that you can't have two non-zero things that multiply together to give you 0. So here's the trick. So we're going to prove this by induction. On the degree of f. So if you have a polynomial of degree 1, so degree 0, this is an empty statement to say that, not an empty statement. I'm assuming that f is non-zero. This would be just silly. If f were the 0 polynomial, everything would be a root, but the degree would be minus infinity or whatever. So I'm assuming it's non-zero. So if it's constant, that is degree 0, then it has no roots because it's a non-zero constant, and 0 is less than or equal to 0, so that's good. And for 1 as well, if f has degree 1, it's the polynomial x minus alpha, and that has exactly one root, namely alpha. nothing else can possibly satisfy x minus alpha, right? So this is true even in a general ring. So this is true if the degree of f is less than or equal to 1. All right? So, and I'm going to do induction on the degree. So now if I take any polynomial of degree less than n equals the degree of f, so now assume true for all polys of degree less than n. So take any polynomial of degree less than n, this statement is true. And now I need to prove it holds for this polynomial f of degree n. Okay? And my proof, no matter what it is, it can't possibly work in the case when I replace k by z mod 8z. You have to be suspicious of that. All right? So here's what we're going to do. Suppose alpha is a root. Alpha in k is a root of f. So then, what does that give you? Well, let's consider f of x, which is exactly the same thing as f of x minus f of alpha. They're the same because f of alpha is 0, after all. So now if you write, let's just write f as an x to the n plus an minus 1 x to the n minus 1 plus dot dot plus a1x plus a0. So I'm just going to literally write this out and factor out x minus alpha. So I'm avoiding, I'm like using very little. I'm just going to do basic algebra. I'm not even going to use the division algorithm or anything to prove this. So you'll be utterly convinced that I'm not tricking you, okay? So this is really, really showing every possible detail with nothing assumed. So this polynomial starts out x to the n, an x to the n, and this one starts out an alpha to the n. So I'm just going to write that as an x to the n minus alpha to the n plus an minus 1 x to the n minus 1 minus alpha to the n minus 1 plus dot 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 plus a1 x minus alpha plus a0 1 minus 1. Okay? I mean, really, I've just done basic algebra at this point. However, notice that, and then here's kind of the trick, or one of the tricks, x to the n minus alpha to the n, you can write that as, we're going to use this factorization repeatedly, this difference of nth powers. You can factor out x minus alpha, and then you have something else. So let me just write that down very clearly right here. X to the n minus alpha to the n is equal to simply an algebraic fact that it's the same as x minus alpha times x to the n minus 1 plus dot 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 plus alpha to the n minus 1. Right? Because if you, did I write that right? Yes. So I mean, if you just multiply it out, you get x to the n plus all this other stuff minus alpha times, so you get x to the n plus x to the, I should probably write more cross terms, but it's just exactly so that things cancel out, it kind of telescopes, and then you end up with this. So the very first term you write out, and the very last term are what's given here, and then everything else in the middle cancels out. Okay? So the next term is x to the n minus 2 times alpha. When you multiply it by x, you get x to the n minus 1 times alpha, which cancels with the other alpha times x to the n minus 1. Okay? Pretty straightforward. And so we'll just use that right here. So we're going to write this as an x minus alpha x to the n minus 1 plus a whole bunch of stuff plus alpha to the n minus 1. And then we'll do something similar for all the other terms. An minus 1 x minus alpha times x to the n minus 2 plus plus alpha to the n minus 2, etc. all the way down to a1 times x minus alpha. And then a0, I don't even care about it because it's just 0 right there. It's just 1 minus 1. Okay? And now, clearly, you can write this as x minus alpha times some other polynomial, because every single term there is divisible by x minus alpha. So this is x minus alpha times some polynomial g of x. And that other polynomial g of x has degree n minus 1, or less, but it really has degree n minus 1. So g is a polynomial in k adjoint x, and the degree of g is equal to n minus 1. Okay? So I've done this sort of showing all the algebra just in a very elementary way, not using the division algorithm or anything, because we have to be very careful that we're not sweeping something subtle under the rug. So, although if you wanted and already knew that the division algorithm, like the division and remainder process, the Euclidean algorithm has an analog in a polynomial ring over a field, so you could use that. But anyways, we have now that f of x is x minus alpha g of x. But, look, by our inductive hypothesis, g has at most n minus 1 roots. This has at most 1 root, and so the number of roots of f, any root of f has to be a root of one of these two factors. So it has to be in the union of a set of cardinality n minus 1 and a set of cardinality 1. So that point right there, when I said that any root of f has to be a root of one of these two factors, that's where I used that we're working over a field. Okay? That's not true if you're not working over a field. So let me just belabor that point a little more. So up, if beta in K is a root of f, then what do you have? You have 0 is equal to f of beta, which is equal to beta minus alpha times g of beta. Beta minus alpha, well, let's say that beta is not equal to alpha, so it's some other root besides alpha. If beta is not equal to alpha, then beta minus alpha is a non-zero number in our field. In a field, every non-zero number has an inverse. And so you could just multiply both sides through by the inverse of beta minus alpha, because we're in a field. You get that 0 equals g of beta. Okay? So if beta is not equal to alpha, beta is a root of g, and this use that we're in a field, and g has at most n minus 1 roots. So less than or equal to n minus 1 roots. And so that tells us that f has at most n roots. Okay, so a polynomial over a field has at most n roots. And this proof is completely false, again, if you replace a field by a ring such as z mod 8z, where you can easily have a polynomial of degree 2 that has 4 roots. Good?
Can you give a numerical example for beta and alpha and 8z?
Well, it's false there, but yes, so an example of a product of two things. So let's see. I mean, the main problem here with z mod 8z is you have 2 times 4, which are both non-zero equals to 0, mod 8. So if you just come up with a polynomial where, let's see, we could just make alpha equal to 0, so the x is going to be 2, I guess we can make the g be 2 times x. Yeah, so alpha equals 0, beta equals 2. I mean, so the polynomial, what do you mean by a numerical example? I mean, it's just if you...
I think that's good enough.
Okay, cool. So there's an example. But the key point is that you have, when you have lots of situations where you have 2 non-zero elements that multiply together to give you 0, then you'll end up with polynomials, not surprisingly, that have way too many roots. Okay? So now, henceforth, we get to assume this fact. And now, all we have to do is combine this fact with Fermat's little theorem and a little bit of thought, and we'll see that there has to be a generator of fpstar. It has to be a cyclic group. It's a pretty powerful structural result. We can't get any further really understanding the Legendre symbol or quadratic reciprocity without this. So let's do it. So z mod pz star is cyclic. That's our goal. I guess it's right here. Here's how we're going to do that. So remember Fermat's little theorem. Maybe I should do it lowercase. FLT tells us that if you take an element A and raise it to the power of p minus 1, it's congruent to 1 mod p, assuming it's not divisible by p. So this is for any integer a with p not dividing a. Okay, remember that from a long time ago? So you have that. And what does that tell you? Well, it tells us that the polynomial x to the power of p minus 1 minus 1, which is in fp adjoint x, has a lot of roots. Namely, every single non-zero element of fp is a root of this polynomial. Because that's literally what Fermat's little theorem says. It says every non-zero element of fp is a root of the polynomial x to the p minus 1 minus 1. On the other hand, so FLT implies that this has at least p minus 1 roots. I guess there's only p possibilities and 0 isn't a root, so it has exactly p minus 1 roots. In fact, don't worry, we will use that. I'm going to use that just now. In fact, exactly p minus 1 roots. So the polynomial x to the p minus 1 minus 1 has exactly p minus 1 roots. So that doesn't give us that fp star is cyclic. However, it kind of helps a lot. So what we'll do, we have to do an additional trick. But it's kind of a step in the right direction. So here's the idea. Let's say you want to figure out how many elements have order p minus 1. What you could do is you could take this polynomial, every root of it is an element of order that divides p minus 1. Now what if you considered a polynomial like x to the p minus 1 over 2 minus 1? If you have that there's roots of this that aren't roots of this, then you get elements whose, it just tells you something about the order of such an element. Okay, so if something's a root of this but not a root of this, then it tells you that, that when you raise it to the power of p minus 1 over 2, you don't get 1. So it gives you information about the order. So if alpha is a root of x to the p minus 1 minus 1, but not of that, then alpha to the p minus 1 equals 1, but alpha to the p minus 1 over 2 is not equal to 1. And that could potentially tell you a lot about the multiplicative order of alpha. So that's the general idea, and now here's how we do it concretely. So let's take the number p minus 1 and factor it as a product of primes. And then we're just going to do a little counting argument, and then we'll get it. So here's how it works. So a precise statement. If d divides p minus 1, then the polynomial x to the power of d minus 1 has d roots. So I just convinced you of that very easily. Fermat's little theorem says that when d is p minus 1. So let's do it for general d. So of course it has at most d roots because of the statement I just erased. And so why does it have why does it have to have lots of roots? Well, it's because it's a divisor of x to the p minus 1. X to the d minus 1 divides x to the p minus 1 minus 1. And you could see that by just factoring this appropriately. It's just, you just write this as x to the p minus 1 over d to the d minus 1, and then you factor out from x to the d minus 1, x minus 1. Okay? This exact idea, I just used it. I'm going to use it again, again, and again, and again. Namely, that x to the n minus 1 factors. Has an x minus 1 that factors out. So I'll use that in every possible imaginable way for this and also for proving quadratic reciprocity. So get used to the fact that x minus 1 divides x to the n minus 1, which I'm sure you're already really used to. We're going to use that a lot. Okay, so x to the d minus 1 divides x to the p minus 1 minus 1. This has p minus 1 roots. This has, at most, d roots. And so, I mean, if it had strictly less than d roots, you'd be in big trouble, because this one has the number of roots equal to its degree. If this had strictly less, then you'd have trouble. So, more precisely, you can write x to the p minus 1 as x to the d minus 1 times some other polynomial g of x, where the other polynomial has degree p minus 1 minus d, which is the other degree. So, how many roots? So you get an upper bound on the number of roots that g has. It has at most p minus 1 minus d roots. This one has at most d roots. Any root of x to the p minus 1 has to be a root of one of these two. So, at least one of these two. If it's not, if you have some alpha over here that's not a root of either of these, then when you plug them in, you don't get 0 on either side. So when you multiply them together, you don't get 0. So it's not a root over here. So any root of the left-hand side has to be a root of one or the other. This one has at most d roots. This one has at most p minus 1 minus d roots. And you get these two numbers. One's less than or equal to d. One is less than or equal to p minus 1 minus d. And they add up to p minus 1. And therefore, both of the numbers have to be d and p minus 1 minus d. So this has to have d roots. And also the other one has to have p minus 1 minus d roots. Okay? So x to the d minus 1 has exactly d roots. All right, so what does this have to do with fp star being cyclic? Well, just think of what we have now. We have a gadget that, given any divisor of p minus 1, gives us a polynomial with the number of roots equal to that divisor. And it's that polynomial right there. So I'm going to use this to construct a whole bunch of elements of fp star with the property that when I multiply them all together, the result will have to have order p minus 1, which will prove that there's a primitive root, without it all actually constructing it, of course. Okay, I'm going to pause. Any questions? Basically, everything I've done so far was to make it so I can say, given a divisor of, given a divisor of p minus 1, give me something. And then I can use that something, namely this polynomial that has lots and lots of roots, to construct a whole bunch of elements of fp star with various orders, and hence conclude that there's a generator of fp star, really proving a structure theorem for fp star. Okay, so now let me show you how this works, finally. And so far we've used just some basic facts about polynomials, that every element of fp star has an inverse, and Fermat's little theorem. So now finally, this is what I'm going to prove. So theorem, fp star is cyclic. Okay, so here's how the proof works. Proof, write p minus 1 as a product of prime powers. Product I equals 1 to t, qi to the ei. Okay, and these are prime powered. These are distinct primes. Okay, so we've written it that way. Now, guess what my d is? It's going to be q sub I to the e sub I. So consider x to the power of qi to the ei minus 1. How many roots does this polynomial have in fp? According to that proposition, how many roots does this have? Exactly, qi to the ei. It has to have d is a divisor of p minus 1. So we just use the proposition with d equal to qi to the ei. And we know that this polynomial has qi to the ei roots. Okay, now I'm going to write down another polynomial, x to the power of qi to the ei minus 1, And it has how many roots? It's like, exactly, qi, the ei minus 1 roots. Also, remember the thing that I promised I'm going to use like crazy everywhere, namely that x minus 1 divides x to the n minus 1, which you can use with, if n is composite, you just replace x by x to that power and you get similar relation. So if it were x to the mk minus 1, if the x to the m minus 1 divides it. This polynomial divides that one. So these roots are a subset of these roots. And q sub I to the ei is strictly bigger than q sub I to the ei minus 1. So voila, the top polynomial has roots that the bottom polynomial doesn't have. And that right there is the key thing in this whole proof. This guy at the top has roots that the other one doesn't have. So let me just call these f1 and f2. f1 has a root, say alpha I, that f2 does not have. And I'm extremely excited about this because, think about it, this root, that's a root at the top and not the bottom, it has the property that when you raise it to the power of qi to the ei, you do get 1, but if you raise it to the power of qi to the ei minus 1, you don't get 1, because it's not a root of the second polynomial. And what that tells you is that the multiplicative order of alpha sub I is qi to the ei. Because if you have any power of your element giving you 1, then the multiplicative order has to be a divisor of that power, and the divisors of qi to the ei are exactly the powers of qi. And if you go down even 1, you don't get 1 when you raise to that power. So this has to be the order of alpha I. So alpha I has order qi to the ei. Okay, so now if you just think of your fp star out there, for every single prime power that exactly divides p minus 1, there is an element of that order. There must be. And now you just take all those elements, take one for each of the prime powers dividing p minus 1. Just choose one element, alpha 1, alpha 2, alpha 3, multiply them all together, and that gives you an element of order p minus 1. So, write down that final step. So finally, consider G, which is alpha 1 times alpha 2 times all the way up through alpha sub t, where alpha 1 has order q1 to the e1, alpha 2 has order q2 to the e2, alpha t has order qt to the e sub t. Consider that element G in fp star. It is a generator for fp star. Claim G generates fp star. Okay, does that seem plausible? It's just that if you have elements of co-prime order, q1 to the e1, so alpha 1 has order q1 to the e1, alpha 2 has order q2 to the e2. Those orders have nothing to do with each other. When you in an abelian group, namely the multiplicative group of fp, when you multiply elements together of co-prime order, the resulting element has order the product of the two orders. So this G has order the product of all these qi to the ei's, which is exactly p minus 1. G generates fp star because G has order q1 e1 times ... qt et. And again, to see that, you have to just prove that if you have two elements of coprime order, when you multiply them together, the order is the product of the two orders. And to see that, it's just, it's yet another little, it's a completely general group theory statement. And to see it, you just note that the product of the two orders, so I guess if I take alpha 1 and alpha 2, notice that if I raise it to the power of q1 E1 times Q2 E2, then you can reassociate and you get alpha 1 to that power and alpha 2 to that power, you definitely will get 1. But if you take any strict divisor of this and try to raise this to that power, then you can just do some little argument, and it's in the book, and you'll get that you don't get 1. And therefore, the order is the product of these two numbers. Okay? I do not feel like giving you every detail of that argument. Okay? Unless you really, really want me to. But it's like written right down in the book. So the product of elements of coprime order has order the product of the orders. So G generates fp star. So that's why fp star is cyclic. fp star is cyclic because, in short, because you take p minus 1, you factor it as a product of prime powers. You look at each of the polynomials, x to that prime power minus 1. It has that many roots. You look at the other polynomial, x to the qi ei minus 1, it has less roots. That tells you that there has to be a root of the first polynomial, but not the second. That root has order qi to the ei, exactly, and you just take all those and multiply them together. And the reason that these polynomials have such easy to understand roots is because of Fermat's little theorem, which tells us that everything's a root of x to the p minus 1. And on the other hand, you also get this sort of upper bound on the number of possible roots. So you get that each of these has exactly the number of roots given by its degree. Okay? And again, I want to emphasize that this whole argument works the same in any finite subgroup of any field at all. Like you could take any collection of, if you take a set of complex numbers that's closed under multiplication and inverses and is finite, it will have to be a cyclic group. There'll have to be one complex number, so all the other ones are powers of that one. The same argument would give you that. You would just say, it's not p minus 1, but what's so special about p minus 1? We didn't use that. This is just, if you had a collection of complex numbers of cardinality n, you put n here, factored as a product of prime powers. For each of the prime powers that divides n, you would use the same argument. Over the complex numbers, you would replace Fermat's little theorem by the fundamental theorem of algebra, which tells you that a polynomial of degree d has d roots, counting multiplicities. So all this stuff generalizes to any field at all. Okay, questions about this? Very, very useful thing. If you think about it, often, if you just want to now you know that if you take fp star, that there's one element in there, so every other element is the power of it. Okay, now I'm really going to wait for questions. Since I keep saying questions, then interrupt, then not giving you a chance. You will never find out about quadratic reciprocity if you don't ask the question.
Can you show us an example with a low prime?
Okay, what is the smallest prime? 2. F2 star is cyclic. That's a really basic example. It has order 1. We want an example where it's not obvious. So let's see, maybe you need p minus 1 to not be square free, I think, because otherwise any abelian group of square free orders is just cyclic anyways. So what? 13 will do. So F13 star, this is an abelian group of order 12. So it's a miracle that there's one element in there that generates the whole thing. It's not just guaranteed by it being an abelian group of order 12. There's all kinds of abelian groups of order 12 that are not cyclic, like Z mod 2Z direct sum Z mod 6Z. So this is an example of an abelian group of order 12 that cannot be generated by any one element. But F13 star can be, and I do not know off the top of my head a generator, and the proof didn't at all guarantee us a specific number, like 2 or something. 2 works sometimes and not other times. However, you could illustrate the proof. You could take 13 and factor it, 13 minus 1, sorry, and factor it as a product of prime powers. So right here, 13 minus 1 is 12, so we have 2 squared times 3. And so if we wanted to explicitly construct a generator of F13 star, then you could take and try to find an element of order 4, so a root of x to the 4th minus 1, and then try to find an element of order 3, root of x cubed minus 1, and then multiply those two roots together, or those two roots together, and you would get an element that would have to have order 12. Because 3 and 4 are co-prime. So how do you find a root of, like, you know that there's a root of this, but you have to actually find it is a completely different question. And typically the way you find a primitive root is you just try 2 and see whether it is or not. If it isn't, then you try 3. If it isn't, you try 4. So it's kind of silly. But you could find roots of each of these polynomials. They have to be there. It's kind of tedious to do by hand. But it's 1, 2, 4. Just computing the powers of 2. 8, 3, 6, minus 1. So it looks like 2 actually does generate, because I just computed a bunch of powers of 2, and I got more than 6 different things. So since the subgroup generated by an element is a subgroup, and the order of a subgroup divides the order of the group, then 2 happens to generate. But if you were to take 2 and raise it to the power, so it has order 12, so if you take 2 and raise it to the power of 3, then the resulting element has order 4. So 8 would be a root of this. So is it true that 8 to the power of 4 is 1 mod 13? I don't know, but it should be. And likewise, 2 to the power of 4 should be a root of x cubed minus 1. So should be. Alright, so that's a small example. Alright, so the next thing I want to show you in my 3 minutes is an application of this. So remember the Legendre symbol from last time, A on P, the symbol A over P. And this is 0 if P divides A. It's 1 if A is congruent to a square mod P. And it's minus 1 if A is not congruent to a square mod P. Okay, so here's the claim. This is exactly the same as A to the power of P minus 1 over 2. I should say it's congruent to A to the power of P minus 1 over 2 mod P. Which I think helps a lot to demystify this symbol. So if you take the number A and raise it to the power of P minus 1 over 2, you get some number mod P. P is an odd prime here. And that number is congruent to, I claim, either 0, 1, or minus 1. Okay? So let me explain why this is easy to see now that we know that fp star is cyclic. But I think not easy to see otherwise. So first note that if you take a to the p minus 1 over 2 and square it, you get a to the power of p minus 1. And that is congruent to 0 or plus or minus 1. Actually, that's just congruent to 0 or 1. Because Fermat's little theorem. It's just Fermat's little theorem. So a to the p minus 1 is either 0 or 1. It's 0 if p divides a, otherwise it's 1. Right? It's just Fermat's little theorem again. So that means that when a is not divisible by p, So just as a consistency check here, so if P does not divide A, so if P does not divide A, then A to the power of P minus 1 over 2 is a root of x squared minus 1, so it's equal to plus or minus 1. Because those are the roots of x squared minus 1. A statement that would make absolutely no sense before we did before. Okay, so I ran out of time, and we'll conclude on Friday. But in case you're curious, all you do is you write down the powers of a g, and you square them all, and then you'll notice that it's exactly the even powers of g that are the squares of g. It's not surprising, and the odd powers of g are the non-squares. And if you look at this, you see that you just see that this holds for g to an even power or g to an odd power. It's just very easy to directly check this statement when you're only checking it when a is equal to g to an even power or g to an odd power. It's just really straightforward to check. It's really hard to see why this would equal exactly the right one over here without knowing the fpstar cyclic. But if it's cyclic, it's just follows very easily. Like g to an even power, you have the even there, they cancel out, and you get 1. G to an odd power, they don't cancel out, and you don't get 1. That's how it is. Okay? So next time we'll talk about Gauss sums and a calculation for quadratic that gives us quadratic reciprocity. By next time, I mean next time we have a lecture, because on Wednesday it'll be Dan's talk.